So now we have seen how the reachability analysis performed in the planning graph can be used to compute some simple heuristics. But the problem with A star that remains is that it uses exponential memory. And to address this problem, another algorithm has been developed, which I won't introduce here, which is called iterative deepening A star. This algorithm is also very good, and specifically it uses only very little memory. In fact, it uses so little memory that most of the computer's memory remains unused. And that led to the question, can't we do anything useful with this memory that aids our search? And the idea is to compute pattern databases in advance of our search that we can use to compute heuristics. I will now use the Tate puzzle to illustrate the basic idea behind pattern databases. In the Tate puzzle, we were given a configuration of tiles on a 3x3 grid, and we had to achieve a specific other configuration by shifting the tiles around. There were 8 tiles, and they were numbered 1 through 8. And one way to simplify this problem is simply to remove the numbers from some of the tiles. So we see some of these tiles are marked with a star now, and we've marked the same tiles with a star in our solution. What this means is we still have to get the tiles 1 through 4 into the correct positions, but we can't tell where the other tiles are. As long as there are tiles with a star, those are in a correct place and therefore form a solution. It should be clear that this problem is simpler than the original problem. In fact, it's a sub-problem of the original problem because we only need to achieve a sub-configuration. But what is important here is that the cost of solving the sub-problem, the one where some of the tiles are marked with a star, is less or equal to the cost of solving the complete problem, so the original problem we're trying to solve. And if that is the case, that means we can use the cost of solving the sub-problem as an admissible heuristic for the cost of solving the overall problem. The problem remains, to solve the sub-problem, we still need to do search. It will be in a smaller search space, but in general search is expensive, and we want to avoid this. And here is the idea that helps us avoid search during the computation of the heuristic. What we want to do is we want to pre-compute and store in a database all the solution costs for all possible sub-problems that we may encounter. Clearly, this will take up quite some memory, but that was the idea, that we want to make use of the memory that we have. Once we have got this database, computing the heuristic is simply a database lookup, so it should be possible in constant time, very fast. Then the only question that remains is how we can construct this database that we want to use as a heuristic. And the basic idea is that we search backwards in a breadth-first fashion from the goal state and record the costs of each of the states as we come across them. So because we search breadth first, we know that the first time we encounter a node, we encounter it at minimal depth, and we can just record the depth in our database as its heuristic value. Now, what we've done is shifted the search operation from the time when we need to compute the heuristic to before we try to solve a problem. But the search we're doing is now a breadth-first search, and that is a very expensive operation because we need to search the whole search space in this way, or generate the search space. The good news is we only need to compute this once. So we pre-compute our pattern database once, and then we can solve many problems with the same database. The next question then is, how do we choose the patterns that we want to record in our database? And the answer here is that we start from the available amount of memory that we have. So we take all the memory, we compute how much memory we will need for search, which may be very little, and the remainder is how much memory we have for our pattern database. And then we know that if our original search space had the size of S, then our new search space depends on how many tiles in the search space we mark with a star, and that is, let's say that's the number n. Then we can say that the new search space has the size of the old search space divided by n factorial, because all the permutations of the tiles marked with a star do not matter. So that's roughly the size of the table we'll generate. And for each element, we need to store the state plus a single number that gives us our heuristic value. Of course, there's no point in doing this for the 8 puzzle because the whole search space of the 8 puzzle already fits into memory. So we don't need to store a pattern database. We can store the database of all solutions. But for bigger versions of the same puzzle, for example, the 15 puzzle shown here, or even bigger, the 24 puzzle, this does make sense. So what we see here is an approach to choosing the patterns that we are looking for. And if we try to find a clever heuristic, what we want to do is exploit symmetry in the space. So if we define the pattern consisting of those tiles here, then we can also rotate the puzzle and use them here and here and here. So the same database can be used to compute different values for the heuristic. And we can simply take the maximum of all these because we must get all the tiles that match our patterns into the right positions. But you can easily see that the patterns that we're now checking are actually overlapping. And that's one of the reasons why we have to take the maximum of all the heuristic values here, because this pattern and the next count the same 4 tiles in the heuristic value. And I've just given you the answer to the first question on this slide, which is, can we add the values instead of taking the maximum? And the answer is no, because the patterns overlap, and that would be counting the same moves twice in computing the heuristic. But there is a way to avoid this problem. And the first step towards this solution is to choose the pattern in such a way that when we exploit the symmetry, we don't have overlapping patterns and we don't count the same tiles twice. And an approach for this, for the 24 puzzle, is shown here. You can see a pattern that we're choosing, these 6 tiles. And if we turn this pattern or the puzzle under it, then we get a different area of the puzzle that does not overlap with our original pattern. So that's half the solution. And the other half is when we record a value in our database, all we have to count is the non-star tile moves. So we only count the ones in the pattern and not the stars, because the stars would appear in other patterns as well, and we don't want to count them twice. If we do that, if we choose the patterns to exploit the symmetry non-overlapping and don't count the star tiles when we compute our heuristic, then we can actually add the different values to get an admissible heuristic out of our database. And this approach is called a disjoint pattern database because the patterns are disjoint and we can add the values of the heuristic. Unfortunately, it's not always possible to find disjoint pattern databases that work. One example where this hasn't been found yet is the Rubik's Cube. But where these heuristics exist, for example in the 24 puzzle, they seem to be the best heuristics around at present. Now we have seen how we can use pattern databases to generate heuristics for a specific problem. The question now is, can we generalize this approach to generate heuristics for arbitrary planning problems? Remember, planning problems are given to us as an initial state, a goal, and a set of operators. So it's very hard to see what a generic pattern could look like. But the key idea for generating pattern databases for the 8 puzzle or for generic planning problems is the same. We need to construct abstract problem spaces. For the 8 puzzle, we've abstracted away the names of some tiles. And for generic planning problems, we're going to do something similar. We're going to drop some of the detail from the problem description to create a more abstract problem. Then we're going to solve this more abstract problem, and the solution length for the solution to the more abstract problem is a heuristic for our original problem. So the most important question then is, how do we create this more abstract problem? And the answer is actually quite simple. What we do is we pick some of the proposition symbols that we have in our propositional planning problem. So these are some of the symbols that describe aspects of the state. And out of the complete set of state propositions that we have available, we pick some and drop them from the problem description. So we drop them from the goals, from the initial state, and from the preconditions and effects of all the operators. And this gives us a more abstract problem. This is really all there is to our new abstract problem space. We drop state propositions from the problem description. Now, the question that remains is, which state proposition symbols should we drop from our problem description? And the way we do this determines the quality of our heuristic. And one way to do this works as follows. We divide the set of all state propositions that we have into mutually exclusive and therefore disjoint groups G1 through Gk. So in each group, we find symbols that are mutually exclusive, meaning they can't be true in the same state. So in our dog worker robot example, the symbols R1 and R2, the robot is at location 1 and at location 2, are mutually exclusive and therefore could be in the same group. Now, we may have quite a lot of groups, which means our abstract problem spaces may be too abstract, they may be trivial to solve, and the heuristic information that reveals is almost nothing. So what we do is we divide this into just two sets of symbols, namely those that are in even-numbered groups and those that are in odd-numbered groups. That effectively gives us two abstract problem spaces. So what we do is simply modify the goal by taking, on the one hand, the goals from the even groups, and on the other, the goals from the odd groups. And similarly, for the operators, we intersect their preconditions and effects with the corresponding groups. This gives us our abstract problem spaces, and now we can construct our pattern databases. We pre-compute them as we did for the 8 puzzle. That's how pattern databases can be used for arbitrary planning problems. And the result that we get from this is a heuristic that computes in constant time, because it's just a hash table lookup. And also, the pattern database that we get with this approach is disjoint, so we can add the two values that we get from the even and odd groups. The pattern database is, of course, still slow to compute, but reusable, so we can use the same database to solve multiple problems. But again, the reusability of this database is quite limited, because we cannot change the goal or, for example, increase the number of containers that we have in our dog worker robot domain. For that, we would have to generate a new pattern database.